Hello, I'm finishing section 13.1 on the basics of probability theory. So there's we're bringing back some of the stuff that we did with set theory in chapter 2. There's a lot of set theory involved. So in set theory, we had the universal set U. In probability theory, we have the sample space. We have the sample space S. Then we have sets. In set theory, we have sets of the universal set that can be A, B, etc. In probability theory, we have events. Events E, F, etc. So an event is going to be a set of the sample space. We also have the empty set. They are going to be the same for both. We have the empty set. That's the set with no elements. And in probability theory, we have also the empty set. That means that that's going to be an impossible event. Let's write like this. I'm going to write this. We have an impossible event. So that's an event with no outcomes. That's going to be denoted with the empty set. And we have the complement of A. That's denoted A prime. And the event. So the complement of an event E is the event, or how to say it, this denotes the event that E does not happen. So event E does not occur. That's going to be the complement of E. Okay, so an example with complements. If event E represents that it rains today, then event E or E complement, the complement of E, represents that it does not rain today. Okay, so we have this, we have the properties, the basic properties of probability on page 667. Assume that S is a sample space for some experiment and E is an event in S. Then the probability of E is a number between 0 and 1. Always. A probability cannot be a negative number and it cannot be greater than 1. If your probability is a negative number, it is not correct. If it is greater than 1, it's not correct either. If it is between 0 and 1, it might be correct. Next, the probability of the empty set or the empty event is going to be 0. That's an impossible event. And the probability that something in the sample space happens is going to be 1. Okay, so now we can talk about odds. we did in the first part of this section was about computing probabilities. So now we can talk about odds. We often use the word odds to express the notion of probability. When we do this, we usually state the odds against something happening. For example, the morning of the 2019 Kentucky Derby, Las Vegas odds makers had set the odds against Country House, the eventual winner of the Derby, at 30-1. When you calculate the odds against an event, it is helpful to think of what is against the event as compared with what is in favor of the event. For example, if you roll 2 dice and want to find the odds against rolling a 7, you think that there are 30 pays that will give you a non-7 and 6 that will give you a 7. Therefore, the odds against rolling a total of 7 are 30-6. We can write this as 30:6, or we can reduce it like a fraction, as 5-1. So sometimes you might see odds written as a fraction, such as 30/6, but for the most part, we will avoid using this notation. So that's the definition of odds. If the outcomes of a sample space are equally likely, that is, every outcome has the same probability, then the odds against an event T are simply the number of outcomes that are against T compared with the number of outcomes in favor of E occurring. We write these odds as N of E complement to N of E, where E complement is the complement of event E. So I'm going to illustrate this with an example. So that looks like a lot of reading, but let me show you with an example how this works. That's, by the way, page 667. And we're doing example 7 on page 668. Okay, a common type of roulette wheel has 38 equal size compartments. 36 of the compartments are numbered 1 through 36, with half of them color red and the other half color black. The remaining 2 compartments are green and are numbered 0 and 00. A small ball is placed on the spinning wheel, and when the wheel stops, the ball rests in one of the compartments. What are the odds against the ball landing on red? And yes, I'm just going to show you the picture. Yeah, that's what a roulette looks like. So it has 36 compartments, half of them red, half of them black, and 2 green compartments with a 0 and 00. Okay, so we know that there are 1 through 36, so 18 black compartments, 18 red compartments, and the last 2 are green. A small ball is placed on the spinning wheel, and when the wheel stops, the ball rests in one of the compartments. What are the odds against the ball landing on red? Okay, so we know that there are 18 red compartments. That means okay, so the event T represents the event that the ball lands on red. And E complement is the event that the ball does not land on red. So the number of outcomes in event T is going to be 18, and the number of outcomes in the complement is going to be 20. So 18 black and 2 green. So the odds against red against the ball landing on red are the number of elements in E complement to the number of elements in E. So those are going to be 2218. Or you can simplify like a fraction, 10⁹. So the odds against the ball landing on red are 10⁹. We also have a probability formula for computing odds. So although we have defined odds in terms of counting, we can also think of odds in terms of probability. In the next definition, we're comparing probability against with probability for. Preferably writing probability as a fraction and then simplifying the quotient of the fractions to obtain the odds. So you may have been surprised that we have not used the A to B notation in this definition of odds. However, we have a good reason for doing this. If the probability of an event E is 0.3, then it's awkward to say that the odds against T are 0.7 to 0.3. It is better to say, well, to find the quotient of probabilities and write this as a fraction. Now we can say that the odds against E are 7 to 30 or 7 to 3. Okay, so that's the probability formula for odds on page 668. And I'm going to do 2 more examples with probabilities and odds. We're doing number 15 and 16. So let me copy those. Okay, so we have the directions. And we have the 2 problems. The first problem is that there's the event that a total of 9 shows when we roll 2 fair dice. Okay, so find the probability of a given event and find the odds of the given event. The sample space. Okay, so event E is the event of rolling a 9. And the sample space is, or the experiment is rolling 2 dice. So the sample space is the total number of outcomes when rolling 2 dice. The number of elements in the sample space, there are 6 ways to roll a single die. So there are going to be, by the fundamental counting principle, there are 36 ways to roll 2 dice. Event T, we have 4 ways to roll a 9. Those are 3, 6, 4, 5, 5, 4, and 6, 3. So the number of elements of E is 4. And the number of elements in E complement so E complement is going to be the event of not rolling a 9. That's going to be 32. So that's the total number of events in the sample space minus the 4 outcomes in E. So part A, the probability of E is going to be N of E over N of S. That's 4/36 or 1/9. And the odds against C. The odds against rolling a 9 are 32-4. So those are 32 ways to not roll a 9 and 4 ways to roll a 9. Or simplify the fraction, 8-1. So we computed the probability of E occurring and the odds against E occurring. In number 16, we have the same questions. We're going to find the probability and the odds against an event happening. So number 16, we have the same question. We're going to find the probability of a total of 3 showing when we roll 2 fair dice and the odds against a total of 3 showing when we roll 2 fair dice. Still, the number of elements in the sample space is going to be 36. And let's call the event F, rolling a 3. There are 2 ways to roll a 3 when we roll 2 dice. Those are 1-2 and 2-1. And the number of elements of F is 2. So the number of elements of F complement is going to be 34. So the probability of rolling a 3, it's 2/36. And the odds, so that wasn't E, that was F. The probability of F is 1/18. And the odds against rolling a 3 is going to be 34-2. So the odds against rolling a 3 are going to be what? Are going to be 34-2. Those are N of F complement to N of F. What is the same? That's 34-2 or 17-1. And the last topic in this section is an application to genetics. Okay, so there's some reading to do. In the 19th century, the Austrian monk Gregor Mendel noticed while crossbreeding plants that often a characteristic of the plants would disappear in the first generation offspring, but reappear in the second generation. He theorized that the first generation plants contain a hidden factor, and nowadays that is called a gene that was somehow transmitted to the second generation to enable the characteristic to reappear. So to check his theory, he selected a characteristic such as seed color. So some peas had yellow seeds and some had green seeds. Then when he was sure that he had bred plants that would produce only yellow seeds or green seeds, he was ready to begin his experiment. Mendel believed that one of the colors was dominant and the other was recessive. That turned out to be the case, because when yellow-seeded plants were crossed with green-seeded plants, the offspring had yellow seeds. And when Mendel crossed these offsprings for a second generation, he found that 6,022 plants had yellow seeds and 2001 had green seeds, which is almost exactly a ratio of 3:1. Because Mendel was skilled in mathematics as well as biology, he gave the following explanation to what he observed. So we will represent the gene that produces the yellow seed by Y, and the gene that produces the green seed by G, by little g. The uppercase Y indicates that yellow is dominant, and the lowercase g indicates that green is recessive. So we have the following picture. So we have two parents. One, parent one with only the Y gene, and parent two with only the green gene. So you can see double Y and double G. So he crossed the two parents for a first generation, and they both contain the yellow-green gene. But the yellow gene is dominant, so they all had yellow seeds. So then when he crossed to first generation plants with both the yellow and the green gene, the following happened. For the second generation, the first one had two green genes or two yellow genes. Another one had, or two had one yellow, one green, and only the one that had two green genes had green seeds. So there is something called a Punnett square. The following is an example of a Punnett square. So we cross to first generation plants that contain both the yellow and the green seed, and only the one with two green genes has green seeds. So the probability that the plant has green seeds is going to be 1/4. Among these four, only the one with two Gs has green seeds. And the probability that the plant has yellow seeds, so as long as it has one yellow gene, it's going to produce yellow seeds. So that is 3/4. So only the one with two green genes will result in green seeds. So I will finish with an example of Punnett squares. That's example 9. Okay, so we have the statement and we have the questions on the next page. Okay, so there's that. And finally, the questions. There are two questions. And now we can read the problem. This on pages 671 and 672. Or 670, 671. Sickle cell anemia is a serious inherited disease that occurs more often in African American babies than in non-African American babies. A person with two sickle cell genes will have the disease, but a person with only one sickle cell gene will be a carrier of the disease. So that person will be a carrier, but will not have any symptoms. If two parents who are carriers of sickle cell anemia have a child, what is the probability of each of the following? That the child is sick with sickle cell anemia, that the child is a carrier, and that the child is disease-free. So we're going to give names to the genes. We're going to let S denote the sickle cell gene, and N is going to be the normal gene. From the context, we can see that the normal gene, well, no, I'm not going to say dominant gene, but this is what we have. On the Punnett square, we have the first generation parent, we have parent 1 and parent 2. And it says two parents are carriers. So both parents have a sickle cell gene and a normal gene. So these are the scenarios, the 4 scenarios. That a child has 2 sickle cell genes, that it has a sickle cell gene and a normal gene, or normal and sickle cell, or both normal. So remember again, a person with 2 sickle cell genes will have the disease, but a person with only one will be a carrier. Okay, so one with 2 genes has the disease. One with 1 gene will be a carrier, and one with 2 normal genes is going to be disease-free. Part A, the probability that the child has sickle cell anemia is going to be 1/4. Of those 4 scenarios, that can only happen once. The probability that the child is a carrier there are 2 scenarios, SN or NS, so that's going to be 2/4 or 1/2. And the probability that the child is disease-free, given that both parents are carriers, is going to be 1/4. Okay, so this is it. This covers the first section of chapter 13. Thank you for listening.